For example 9, notice that we have two polynomials, and we're finding the derivative. Now, prior to this lesson, it would have not been fun to apply the limit definition to each one of these, right? We could do it. It would just not be enjoyable in any kind of way, right? But what we have when we have polynomials, notice that we have individual functions where we have the difference of these functions added to a constant function. Well, we have a rule for constant functions, we have a rule for power functions, and then to add and subtract these things up, it's a combination of the constant multiple rule and the sum and difference rule. So when we take the derivative of polynomials, we're using all of the derivative rules that we've come up with so far. It's going to be easy. Watch. It's not even going to take that long. This video is going to be seconds long. Actually, no, it's going to be longer than that. But still, let's scroll down here and take some derivatives. Watch this business. You ready? F prime of x should be equal to, leapfrog that 3 down, 3x squared, minus 4x, and I'm done with that one. It's done. It's finished. Okay, let's go over here to this g of x function. So g prime of x should be equal to, leapfrog the 4 down, that's going to be negative 4x to the third power, still over 2. Leapfrog that 3 down, but it's going to multiply times the 3 that's already there, so plus 9x to the second power. And then finally, minus 2. Like, think of that as a line, just taking the slope of that line. Now, if you wanted to, you can go ahead and divide negative 4 by 2 to get, negative 2. That'd be good. Wow, look how easy that was. Seconds, I tell you. All right, we're going to do maybe 1 or 2 more examples here. Example 10, find the points on the graph of f of x equals blah, 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 where the tangent line is horizontal. Okay, so this is a very important application of calculus because when we're finding horizontal tangent lines, it means something specific about the original graph. Here's some pictures of this. Let's see what this is look like. And then we'll do the calculus in order to figure out what these things are. Oh, look, the answer's already there. Don't worry, we're going to come up with it. So here at each one of those horizontal tangent lines, what do we have on the graph? We have these relative minimum and maximum points. Calculus is going to give us a way to find those things super easy. We don't have to rely upon a calculator to get them. So let's actually do the math to come up with those numbers. Apparently, there's a square root of 3 involved. Spoiler. Okay, let's add a page to this and let's take a look. Our function here, oh, this is in purple. Let's do purple. Okay, f of x is equal to x to the 4th minus 6x squared plus 4. Oh, it's going to take me hours to take this derivative. F prime of x is equal to, let's see, 4x cubed minus 12x. Ta-da! I'm done. Now, I want horizontal tangent lines. A horizontal tangent line has a slope of 0. M equals 0. So I'm going to take the derivative that we just got, and I'm going to set it equal to 0. 0 is equal to 4x to the 3rd minus 12x. And I have a cubic polynomial. How do I solve these things? I solve it by factoring and applying the zero product property. So I can see that these things have a common factor of 4x. So pull it out. So 0 is equal to 4. Whoops, I forgot the x. And then I'm going to have x squared. And then when I pull out a 4 of this one, this is going to be minus 3. Okay, and then I set each of these guys equal to 0. Like this one, not even going to bother doing anything, just x equals 0. There we go. And then over here, x squared minus 3 is equal to 0. Add the 3 over. X squared is equal to 3. Take the square root. And there's 2 square roots to any number, a positive and a negative right there. Now, let me go back to the original one. It says points. Find the points. This means x comma y. Not just the x values. Sometimes it just says the x values. This one says points, so pay attention. So, like, how do I get the x or the y values for each one of these? Okay, well, 0 is going to be real easy. If I plug 0 into this function, 0, 0, I just get 4. So here I've got 0, 4. All right, well, What about the y values for the other ones? Well, okay. So let's see if we can handle this. Let's see. We got f of the square root of 3. We're plugging it into the original function. I have the square root of 3 to the 4th power minus 6 square root of 3, which we're going to square, and then we're going to add 4 to it. Okay, man, we're going to do this without a calculator? If you say so. Well, I'm going to think of this square root of 3 to the 4th as the square root of 3 squared, because the square root of 3 squared is 3, and then 3 squared is 9. Wow, look at that without a calculator. Again, the square root of 3 squared is not 9, it's 3. And then 3 times the negative 6 is a negative 18 plus 4. And then I've got 9 minus 18 is a negative 9 plus 4. Gives me a negative 5. Hey, I wonder. Is that what they got? Oh, it is what they got. We got it right. And then since this is an even function, look, it is an even function. Boom, boom. When I plug in a negative number, I get the same exact thing as when I plug in a positive number. So the y value of negative 5 is going to also be true for the negative square root of 3. And I can see that in my little answer, my answer that I just checked my work with. Fantastic. All right, we're going to do just one more example. Please, I beg you, just one more. Yes, let's do one involving some rectilinear motion. The position of a particle moving along a line is given by s of t is equal to, and then I got a cubic polynomial. I'm not going to read it off. Where s of t is measured in meters and t in seconds. Find the acceleration of the particle at t equals 2 seconds. How do I find the acceleration if I'm given position? I have to find 2 derivatives. This is going to be super easy because it's all polynomial. And I can find derivatives of polynomials all day. I'm going to do it right here. And you know what? There's not a whole bunch of space. It doesn't even matter. I don't even care because I'm not going to need it. So s prime, I'm still using purple apparently. S prime of t, that's your velocity function. And my velocity function is going to be, let's leapfrog that 3 down, 6 t squared minus, leapfrog the 2 down, 10t, and then finally plus 3. How do I find the acceleration function? Well, I take the second derivative of t, which is the first derivative of velocity, in order to find the acceleration function, which is going to be 12t minus 10. There we go. And now let's go ahead and plug in 2 like it asks us to do. So this should be a of 2 is equal to 12 times 2 minus 10. That's 24. Minus 10 is 14 something. Let's figure out what the units are. Okay, so here's the way I would suggest doing it, just simply because, like, outside of acceleration and particle physics and rectilinear motion, you may have to do the same kind of thing in the context. So I'm just going to look at the units that we started with. So when we take s prime of t, so think of this as slope, where we have a change in y over a change in x. So for this one, the change in y, the y coordinates are s of t, which is measured in meters. So I have meters on top. And then on the bottom, I have, well, our t values that are changing, those are in seconds. So it's in seconds. Okay, so meters per t. Yeah, that's silly. Meters per second. Okay, so now when I find the second derivative of t, this is the change in the first derivative over a change in time. Okay, so the first derivative was changing by meters per second, and then our time is changing by seconds. And then we usually write that, of course, as meters per second, or meters per second squared. Meters per second squared. And there we have it. There is the first objective concluded, where we were able to come up with the constant derivative rule, constant multiple, the power rule, and the sum and difference rules. And when we put it all together, it allows us to easily and quickly find the derivative of any polynomial function.